All right, we're about to tackle one of the biggest, most fundamental questions you could ever possibly ask. This isn't just about stars or galaxies. No, this is about the very fabric of reality itself.
No, really, think about that for a second. Why is there all this stuff, this universe with you and me and everything in it, instead of just an empty void? The wild part is, our best understanding of physics says there should be nothing. And the key to this whole cosmic mystery? It lies with a ghostly twin to all the matter we know.
Okay, so let's set up the cosmic crime scene. The theory is pretty clear. The Big Bang should have created equal amounts of matter and its perfect mirror image, antimatter. But here's the catch. When matter and antimatter touch, they annihilate each other. Poof. They vanish, leaving behind nothing but a pure flash of energy. So logically, the universe should be a completely empty, boring bath of light. But it's not, is it? We're here. The stars are here. All the antimatter somehow is missing in action. So the billion-dollar question is, where did it all go?
To crack this case, we have to rewind the clock, back to a time before anyone had ever seen a single speck of antimatter, because this stuff wasn't discovered in a lab with test tubes and beakers. No, it was first found hiding out inside an equation, a ghost in the math.
So, back in the 1920s, physicists was riding high on Schrödinger's equation. It was a pillar of quantum mechanics, and it worked beautifully for describing simple, slow-moving particles. But when scientists tried to use it on heavier atoms, like gold, the whole thing just fell apart. The math just didn't work. And the reason is that in those big atoms, the electrons are whipped around the nucleus at insane speeds, getting close to the speed of light. And Schrödinger's math? Well, it just couldn't keep up.
And this is where a quiet, brilliant physicist named Paul Dirac steps onto the stage. In 1928, he came up with a new equation, and it was a masterpiece. It managed to beautifully stitch together quantum mechanics and Einstein's special relativity into one. For the very first time, we had a single piece of math that could describe an electron, no matter how fast it was going.
And that's really the key to understanding Dirac's mind. He was driven by this deep, profound belief in mathematical beauty. He just felt that the universe's rules had to be elegant, and his hunt for that elegance led him to a prediction that would shock the world.
The problem was, in a way, almost comically simple. You know how the equation x squared equals 4 has two answers, right? Positive 2 and negative 2? Well, Dirac's beautiful new equation also spit out two solutions. One of them was perfect. It described the electron we all know and love with positive energy. But the other solution, it described something that seemed impossible, a particle with negative energy. It was this mathematical ghost that nobody knew what to make of. Dirac had accidentally predicted a perfect twin to the electron, but with the exact opposite charge, an anti-electron.
For 4 years, this anti-electron was just a phantom, a weird little quirk in the math. A lot of physicists thought, well, the theory must be flawed. But then, theory made first contact with the real world.
In 1932, a physicist, Carl Anderson, was just doing his thing, studying powerful cosmic rays zipping in from space. He was watching their tracks as they passed through a magnetic field, and he saw something that made him do a double take. He saw a particle that curved the wrong way, the opposite way an electron would, but it was clearly the exact same mass. It was Dirac's ghost, a real-life, positively charged electron. We call it a positron now. A prediction made with just a pen and paper had just exploded into reality.
And this new particle had a truly mind-bending property. When it ran into its normal matter twin, an electron, they would both just vanish in a brilliant flash of energy. This process, annihilation, is hands down the most efficient energy conversion we know of. 100% of their mass gets converted into pure energy, a perfect, real-world example of Einstein's E equals mc squared.
So this brings up a huge practical problem, right? If antimatter annihilates the very instant it touches anything made of normal matter, how on earth do you hold on to it? I mean, how do you build a bottle for something that destroys the bottle itself on contact?
Well, believe it or not, at places like CERN, scientists have become master antimatter wranglers. They use this incredible machine, the antiproton decelerator, to make and slam the brakes on antiprotons. Then they gently mix those antiprotons with positrons, coaxing them to form little atoms of antihydrogen. Now, since these antiatoms are neutral, you can't hold them with electricity. But, and this is the genius part, they are slightly magnetic. So scientists can suspend them in this incredibly complex magnetic bottle, holding them in a near-perfect vacuum so they never, ever touch the walls.
But let's talk about production. Just how hard is it to whip up a batch of this stuff?
Well, with all the power and technology at CERN, they can produce about 1/1000th of a gram per year.
So at that rate, if you wanted to make just a single gram of antimatter, you'd have to wait for about 1 billion years, give or take.
And the cost? Oh, the cost for that 1 gram, you might want to sit down for this. It's estimated at around 1 million billion euros. It is, without a doubt, the most expensive substance ever created by humankind. So why? Why go through all this insane trouble and expense? Because by finally capturing and interrogating this ridiculously elusive suspect, we might just find the clue that solves our original mystery, the case of the missing universe. The entire goal is to find out if antimatter is a truly perfect identical mirror image of matter. Let's put them in a police lineup. On your left, you've got a normal hydrogen atom, a positive proton in the middle with a negative electron orbiting it. Easy. On your right, antihydrogen, a negative antiproton at the core with a positive positron orbiting it. On paper, it's a perfect mirror image. Same mass, just opposite charges. But is it really a perfect mirror in the real world?
And this, right here, is the whole ballgame. This is the question that drives all this research. Do these two atoms behave in exactly the same way? Do they absorb light at the same frequencies? Do they react to gravity the same way? Or is there some tiny, subtle, almost undetectable difference that could have tilted the scales back in the Big Bang, favoring matter just enough to create the universe we see today?
And this isn't just theory. This is happening right now. Experiments like the Alpha collaboration at CERN are making huge leaps. They figured out how to cool antihydrogen with lasers, which is incredible. They've watched antimatter fall in a gravitational field. Yep, it falls down, not up. They're taking these stunningly precise measurements, comparing antihydrogen to hydrogen with unbelievable accuracy. And so far, they've found absolutely no difference, zilch. They appear to be perfect twins.
And so, after all this work, decades of searching, from the pages of pure mathematics to the most advanced laboratories on the planet, the central case remains wide open.
We've got the suspect in custody, we've built the ultimate interrogation room, and we're asking it these incredibly detailed questions. We have the means, we have the motive, but we still can't explain the crime scene.
Right now, our best theory is that maybe the symmetry wasn't so perfect after all. The idea is that for every billion pairs of matter and antimatter particles that were forged in the Big Bang, some mysterious process created just one extra particle of matter. And after that great universe-clearing annihilation wiped everything else out, that tiny remnant, that 1 in a billion leftover, is what went on to become every star, every galaxy, every planet, and you.
And that leaves us with this final, truly profound thought. Is everything we see just the leftovers? Is our entire magnificent universe nothing more than a cosmic rounding error? A lucky fluke in the otherwise perfect laws of physics? The case is still very much open, and finding the answer could change everything we think we know about why we're here at all.